This is the second part of the lecture on the electric field of a continuous distribution of charge. We'll deal with an example that is slightly more complicated than the rod that we considered in part one. We're going to look at the disk of charge. And we'll jump right to the example. Within the example, we'll talk a little bit more in depth about the qualitative analysis that you should do before starting a problem like this. That reduces the amount of work that you have to do later. And in particular, we'll introduce the idea of a symmetry argument in order to get that simplification. Then we'll talk about how to construct an integral for a ring of charge, and we'll build up that ring into a disk to construct an integral for a disk of charge. And then finally, we'll solve the integral in the end, which is, again, a calculus problem, not necessarily a physics problem. So let's look at this example. The idea is to find the electric field of a disk. That disk, we're going to assume, has uniformly distributed charge of total Q total and has a radius of R disk. And we're asked to find the electric field not everywhere in space, but at a particular point which lies directly above the center of the disk. So we'll be looking for the electric field at that point. So we'll start calculating this in a moment, but we should first try and look at this with some qualitative eyes. And there's a couple of simplifications that we can make due to these qualitative considerations. So one is that a disk is composed of concentric rings. So a good strategy is to think of the disk as being constructed by these rings. So here's one particular ring, and then maybe there's another one all the way out. And if we can figure out what the rule is for a single ring of charge, then we can build up a disk as the sum of the rings. And that just comes again from the superposition principle. If we know what the electric field of this single ring is, and then we add that to the electric field of the next ring and the next ring, then that will give us the answer for the total disk. So we'll do that. We'll first consider the problem of a ring. The reason that that's a nice way to do it is because then you deal with two one-dimensional problems instead of dealing with a two-dimensional problem and a two-dimensional integral. The second qualitative consideration is that the disk has some symmetry. So we'll come to this, but you can see that if you rotate the disk, it remains the same by any angle. You can rotate it by any angle about this axis here, and it will be exactly the same disk. We call that a symmetry. And using symmetries helps us to simplify the calculation. In particular, it eliminates the need to calculate certain components of the electric field. So remember, the electric field is a vector. So if we're asked to find the electric field vector here, we need to give a vector answer. And in three-dimensional space, that could have three possible components, the x, the y, and the z. And in this process of constructing integrals, we actually have to construct three separate integrals for those different components. So if you have some symmetry, then you might be able to reduce the number of equations, the number of components that you need to calculate, and thus the number of integrals that you need to construct. So let's talk about this a little bit generally. We actually dealt with this in the first part of the lecture when we were looking at a rod. In that case, what I did was I said, well, you can look at the chunks and the electric field produced by each chunk, and you can see that, well, we have an electric field produced by the leftmost chunk like that, and by the rightmost chunk like that, and then sort of adding them up as we go, you can just see that the sum of all these vectors will lead to a total electric field vector that looks like this. And that's because of the symmetry of the situation, because we're picking a point which is directly above the center, and because the uniform charge ensures that these two things have opposite values of their x components. So that leads to the understanding that we only need to find the vertical component of the vector as we're doing the calculation. And that's sort of an obvious thing. It's sort of intuitive. But what we want to do now is try and make that intuitive statement more precise. And the way that you do that is something called a symmetry argument, which we'll introduce now and we'll come back to in particular when we're doing Gauss's law problems in the next couple of days. So we want to identify, so the process of making a symmetry argument is to first identify a symmetry of the object. So for the case of a rod, this rod has a symmetry which is due to the plane that intersects it. So you can imagine that you intersect that rod with a plane, goes through the plane right there, and if I were to reflect about the plane, then the rod would be exactly the same rod. The left side would transfer to the right and the right to the left, and it would still be the same rod. In fact, the whole point is that after you do that transformation, you wouldn't be able to tell that anything was done to it. So you could do it behind someone's back, and they wouldn't know if you made that transformation or not. So if you do a transformation and the object remains the same, that's called a symmetry. So we found a symmetry of the rod now. The second part is to state that the electric field produced by the rod, or the object, must have exactly the same symmetry. So, and the reason for that is, if it were not true, then the electric field would be different for the same object. Meaning, for example, if I were to say, well, there's an electric field of the first object, the rod, where the electric field points like this. But then, when I do the symmetry transformation, as I reflect the rod about itself, the E field would be reflected to the other side. And what we would be left with is exactly the same rod, because that's a symmetry, but a different electric field. And that's impossible. You can't have two different electric fields for the same object. So the statement here is, because if it did not, then you would have two E fields, two E fields for same object. That's the basic statement of why part B has to be true. The third part is to then say, well, if I have that symmetry of the electric field, then it implies something about the components. So if we look again at this point that I chose, I was looking at an E field at the point, which is actually the point P that we were talking about before, directly above the center. So if I know that the electric field vector at that point must be symmetric about rotations, then I know that this vector or this vector are impossible. Because, sorry, not about rotations, about reflections. Then these two vectors, either of them would be reflected to the other side and would be changed. So it would not be a symmetry of the electric field. So what that means is that you cannot have any component of the electric field that points out of the plane, and therefore the electric field must point away or towards. So the statement that we get for the rod is E, let's say X, must be equal to 0, such that it has the same symmetry if this is X and Y here. And that means we only need to calculate the EY equation. So that's a symmetry argument, and we will use that in our calculation. So let's look at the electric field of a ring of charge. And our first step in doing a problem like this is to apply those qualitative arguments. So the qualitative argument that we're going to use is that of a symmetry argument. We're asked to find the electric field directly above the center. So we're asked to find the electric field at this point P. You could make a similar argument to what we did in part 1, where you chunk this up and then you say, well, for every chunk that points in one direction, there's a chunk on the opposite side of the ring that points sort of in the other direction, and the non-z components of those electric field vectors, so if I call this the z-axis, the non-z components must be 0. They'll add up to 0. But let's do it as a symmetry argument instead. So qualitative consideration, symmetry. So let's take those steps that we had on the previous page. Part A is to identify a symmetry of the object itself. So what is it? Well, I can rotate by any angle. So rotation of ring by any angle about z-axis is a symmetry. So I could rotate it by 90 degrees. It would still look like the same ring. I could rotate it by 2 degrees. It would still look like the same ring. So any rotation will lead to exactly the same ring. Now we state the E field, in particular at point P, must also have that symmetry. And C, we make a statement about the E field itself, about what kind of components it can have. And you might just sort of like draw a little sketch for yourself. So if we have point P here, and I were to choose an electric field that pointed like this, so let's just make a hypothesis that the total electric field points like this. So is this E? The answer is no, cannot be that, because if it's going to have this rotational symmetry, if I'm going to be able to rotate it without changing the field, you can see that this vector would then rotate around the z-axis and point in a different direction. So that means that E has only an E sub z non-zero, meaning EX and EY, I guess I should write it like this, EX is equal to EY is equal to 0. So the idea is only if you draw an E field along the z-axis will that be unchanged by a rotation. So it could point away from the ring, could point towards the ring, but we already know if this is a positive charge, then it'll point away. So that's our qualitative consideration. And now we want to move on to the quantitative part. And the quantitative part is the construction of the integral. So quantitative and you see, it was important to do that qualitative up front because now our construction of the integral is reduced to only finding E sub z. So we're only looking for the quantity E sub z. If we hadn't done the qualitative part, then we would have to find Ex, Ey, and E sub z. So what is E sub z? Well, we write out the simplest approximation of it, and we're going to do, as we did before, the chunking of this disk, of this ring. We can consider one particular chunk of it, and we'll call that, let's call it Q sub n. And that Q sub n will produce an E sub n. So E sub n is produced there. Let me actually give myself a little bit more space there. So this particular chunk will produce an E sub n that points directly away, because remember we consider these chunks to be point charges, and we know what the field of a point charge looks like. So it's going to look like this. And I might draw a little bit more information here. So one thing is that there's going to be an R sub n, the distance between the point charge and the point where the electric field is being measured. Another thing is that we're going to have an angle here, theta sub n. And theta sub n could depend on the chunk, although we'll see in a second it does not. And theta sub n is also inside here, inside this little triangle. Maybe I should label that, identify that triangle a little bit more clearly. There's a right triangle inside there, which also has the theta sub n in it. So the simplest statement, the first statement, is that the E sub z of the total electric field at point P is simply equal to En sub z, the sum of them. So n going from 1 to capital N. So going all the way around the ring, counting them all up. And that's a very simple statement. The z component of the total is equal to the sum of the z components. We should say it's approximately equal, because again, we're dividing this into small chunks which are not point particles, but it's an approximate statement. So what is ENZ? Well, we want to write a component of a vector in terms of the magnitude of the vector. So as you can see from this picture, the magnitude we would call E sub n, and the component would be this number here if we project onto the axis. So if we had an axis right here. And that number is positive magnitude En, I guess I can write it like this to be really clear, times the cosine of theta n. As you can see, you're projecting onto that axis using the cosine of theta. Okay, next step. Oops. Now we try to replace some of these things. Well, we know what the magnitude of the electric field of a point charge is. It is K, Q sub n, absolute value, over R sub n squared. That is the magnitude. I still have cosine theta in there. Now let's look at that triangle, because I think we can identify what that cosine theta n is. That triangle looks like this. And our theta n looks like this. So cosine theta n, I guess we need to specify how high above the plane we're talking about. This triangle has an h on this side. This is a right triangle, and this is the r. So we have r sub n here, which is equal to the square root of h squared plus r squared, like that. So we see a couple things here. One is that cosine of theta n can be written as h over r sub n. We still have the rest of it, the magnitude of E. And the other thing that we see is that r sub n actually doesn't depend on the particular chunk. It doesn't depend on little n. So in the next line, we can say exactly what r sub n is. I guess I'll put the h up front here and up top. And r sub n is actually equal to then h squared plus r squared square rooted. So this becomes h squared plus r squared to the 3 halves. And interestingly, none of this depends on n except for q sub n. So we actually don't even need to do an integral here. We could do an integral, so I don't think I'll do it, but you could imagine that you could make a delta s here, and you could say that that delta s is actually equal to r times a delta theta in the xy plane. And then you could do an integral. You'd arrive at a Riemann sum which has a delta theta, so that would be an integral over theta. It would be a very simple integral. There's no integrand that depends on theta, and so we would just integrate around. But we don't even need to do that here, because what we have is we have a whole bunch of constants, k, h over h squared plus r squared to the 3 halves. And then we have the sum from n is equal to 1 to n of the q sub n's. We say that these are approximate, but you can see now that this is actually not approximate. The sum of all the chunks is simply just q. So it's the q for that particular ring. So what we get is EZ for the ring is equal to K, H, Q, I guess the Q is positive, so I don't need to put absolute value, over H squared plus R squared to the 3 halves. And that's our result. So that is the electric field of a ring. I could also specify, if I were to stop here, the electric field vector is equal to 0, 0, EZ ring. just to be completely clear, that I've already said from qualitative arguments, from symmetry, that I don't need to find EX and EY, and I've already found the value for EZ. Okay, now the electric field due to a disk. So remember that our first qualitative argument, which we talked about way back at the beginning, was that a disk is actually composed of rings. So if I again call this the z-axis, and then we'll put an x and a y axis here, so x and y, we can imagine, let's remove this R disk here, we can imagine that we can cut this up into chunks, but chunks that are rings. So I'm not going to draw all of them, I'll just draw one of them, and I'll shade it in. So I'm going to choose a chunk which is a ring there. That chunk has charge q sub n, and it has radius r sub n. Then we can talk about, at a distance of h above the disk, what the electric field is due to that particular thing, and we just found it. We found that that should be a vector which points in the positive z direction, and that will be our E sub n in this case. So that's the E sub n for the ring that I've shaded in here. So I can say that, well, I guess I should explicitly say my qualitative argument is that the disk is the sum of rings. So quantitative, I guess I could also say, and the same symmetry applies. So we don't really need to say that, because if we say that it's the sum of rings, then all of those ring vectors, all of these E sub n's, we already found only point in z. If you were to start without looking at the rings, you could make a symmetry argument about the disk, just like we did, but that carries through automatically because we found that the rings have an electric field that only points up. So now let's do the quantitative part. So the quantitative part is to construct the integral, and that integral is, I only need to find EZ, so EZ for the ring is equal to the sum from n is equal to 1 to n, and now these are the rings outward. So you have the first ring on the inside, and then you have the nth ring on the outside, the capital Nth ring on the outside, and that will be the electric field n z of, oh geez, I keep mixing up ring and disk, I'm sorry. So this is for the disk, and this is for the ring. And again, we should say it's approximate because we're chopping into finite chunks. Okay, let's give ourselves a little bit more space. So EZ disk is equal to the sum from 1 to capital N. And now we can say what this actually is. Well, if you look at that E sub n up here, the z component of that vector is simply its magnitude because it points in the positive z direction. So I can make a small step there and say that this z component is just E sub n of the ring magnitude. Next step, we want to say what that magnitude is, and that's what we did the work on the previous page for. We have an expression for E sub z. The magnitude of that is just making sure that that whole thing is positive, and so we get KHQ, and I should say Q sub n here, so let's actually make this capital Q sub n. H, remember, did not depend on the particular ring, and then we divide by h squared plus r squared, but that is going to be h squared plus r sub n squared to the 3/2. Okay. Now we want to understand want to break this down. Remember, our goal is to get to a Riemann sum, so we need to get a delta in there somewhere, and that's likely to come from this Qn here. So what is Qn? Well, I can see that it's a ring, and it's a ring with radius r and with width delta r. So it has radius rn, and it has width delta r. So the value of Qn is going to be a linear mass density multiplied by 2 pi Rn, but maybe that's not the best way to say it because it'll be difficult to find that linear mass density. So instead, let's use the area charge density. So the area charge density is going to be the area of that ring multiplied by sigma, and the area of the ring is going to be approximately 2 pi Rn, the circumference, multiplied by delta r. And then you multiply the whole thing by sigma. And we can just state here that because it's a uniform density, a uniform charge distribution, then sigma will simply be Q total over the area of the total disk, which is pi r total, or r disk squared. Maybe we'll come back to plug that in later. But for now, we can write k, h, and then Qn is 2 pi Rn sigma, and I'm going to put the delta r out front, out at the end. And then we're left with h plus Rn, both squared to the 3/2. So what do we have? We have a Riemann sum. We have a function in here, which depends on r sub n, and we have a delta r out at the end. So what that means is that I can write, if these were all approximate, I can write that it is exactly equal to the limit as n goes to infinity, where this was n from 1 to n, of that whole thing. I guess I won't write it all out. And that limit has a specific symbolic notation associated to it, which is called the integral. So we have the integral, and now I need to write this function not in terms of Rn anymore, but in terms of r. So I have 2 pi sigma kh times r all over h plus r, both squared, to the 3/2. So I don't know how that could be 3/3. It's 3/2. And the delta r becomes dr. Now we have to look at the limits. So the limits, what are we doing? We're integrating outward from the center of the circle to the edge of the circle. So we're going from Rn of 0 outward to here, which is simply r disk. So we're going from 0 to r disk. I'm going to pause here, and then we'll come back and evaluate the integral.